Another thing about atoms that I want to focus on, and it gets a little tricky, is this idea about electrons. And we said, or we kind of briefly said, that actually with the Bohr model of the atom, we know that electrons are not only outside the nucleus in cloud, but actually electrons have a certain what we call energy levels where they reside at a given time. And those energy levels are what we call quantized. So just as you see this person walking upstairs, this person can walk up and be on this stairs at this height. They can walk up and be on this stairs at this height, this stairs at this height. Okay, that person's height can only be at certain elevations, kind of above, I guess you call ground level. That's kind of that person's height is what we say quantized. And so also electrons are, when they are at energy levels or locations in a cloud outside of a nucleus of the atom of their choice, electrons can only be at certain energy levels. The opposite of quantized would be kind of this right here, where we see a person that can be at any elevation. Okay, it's like a continuum of elevations this person can be at. This is not quantized. Okay, so the energy for electrons is quantized. So I think, I can't remember which order, but there's a video that you're going to see that actually kind of shows this like this, and it works pretty good. This could be my atom, and we said at the center of an atom is what? The nucleus. Okay. Now, we said outside the nucleus are the electrons, and now here we're actually showing where electrons can be. Electrons can be here at this kind of relative position with this relative energy. Electrons can be here at this relative location with this relative energy, here or here. As I've drawn those 4 arrows, those are showing 4 different energy levels. Not only are they different energy levels, but they are also different locations outside the nucleus. Now, this is kind of a simplified approach or model, but it does get us down the road. Now, I'm going to put a 1 here, a 2 here, a 3 here, and a 4 for this last arrow. Maybe intuitively, maybe not, but actually, do you guys buy this? That here, to get clear up to this number 4, okay, this actually is the highest energy level. And we're going to see that sometimes, or I don't know if we're going to necessarily focus on it this semester, but when we're trying to, what we say, find homes for electrons, they're definitely going to go clear out there to the highest energy level, because we're going to see that these green ones, the 2, 3, and 4, they have a maximum number of electrons for a given atom. They basically run out of room for electrons. So electrons then actually go up to the next energy level possible if the home is full down here at the low. So this is low energy. Low energy, E for energy. Okay, so hopefully you're kind of getting a sense for what that looks like. So one thing that I do want to talk about, because they're very practical applications for electrons doing this in what we observe for everyday life. Electrons actually can jump ship. This says electrons can absorb some energy, and just on the diagram I showed you a minute ago, an electron can absorb energy and it'll be promoted up to a higher energy level. So that's pretty cool. But now remember that it's quantized. So this jump will kind of show, here's my electron going to jump up, okay? That jump takes a certain amount of energy. And so it's not just, it's kind of like Goldilocks and the 3 bears. It can't be too much energy and it can't be insufficient energy. So it'll be a certain amount of energy for that electron to be promoted. Okay. So actually being shown here, this little squiggly mark here, is the energy that's being sucked in or added or whatever to this electron for it to move up. That's what that little squiggly mark right there is. That's the energy being added, or what we say absorbed. And then of course you see this electron now at energy level 2. If this was 1, okay, it was promoted. Okay, but like I said, it's quantized. So not only is the step it went up quantized, but also this amount of energy, like I said, needs to be just right. Not too much, not insufficient, but just the right amount of energy characteristic for that particular jump. So shown right here then is, you might recognize a prism. We can actually observe, this is so cool, we can actually observe that sucking up of energy if we go ahead and what do prisms do? If I were to ask you, you probably would tell me prisms separate, they give us a rainbow. So they, what we say, separate light, okay, remember, into rainbow. Now, remember we talked about light is actually a wave, and that we talked about light is a type of electromagnetic radiation, and that we talked about that we have these, I'll go ahead and put a red, let's see, RG, Roy G. Biv, so red, orange, yellow, G, blue, indigo, violet. I don't know if you learned it like this, but it's called Roy. That's like a person's name. G as in his middle initial. Biv, B-I-V. I've never known somebody with the last name Biv, but there you go. So if you do that, actually, then you have written out the colors of the rainbow. Of course, we have red, orange, yellow, green, blue, indigo, violet. Now, I wrote them like this because this is what we said the longest. Hopefully you remember this from our physics unit, longest wavelength, and this is the shortest wavelength with regard to visible light. Whew. Anyway, I wrote all of this because actually that's what prisms do, is separate light into its colors of the rainbow. And here we go. This is where this connects, and this is actually kind of important. So remember I said that that little energy, okay, was a specific amount, and it corresponds to actually a specific energy of color. A specific, these different wavelengths are different energies. I think when we studied electromagnetic radiation before, I said that shortest wavelengths of all sorts of electromagnetic radiation, not just visible light, are higher energy, and long wavelengths are lower energy. Whew, hopefully you can read that. So anyway, you can actually catch in action that sucking up. So here we go. See this? Okay, I don't know if you can tell, but it's not a rainbow. It's sort of a rainbow. We see our reds over here and our violets over here and everything in between, but hopefully you can see those black lines. So those dark lines there are what we call absorption lines. Those dark lines were formed because of this sucking up of that particular energy of visible light. Is that not cool or what? Okay, there's kind of a, I forgot I had all these builds. Okay, I'm going to switch it up a little bit. If you were to compare these two pictures, if you're a picture person, hopefully you would see what the difference is. Okay, the difference here is that what it is starting at is in what we call an excited or a promoted energy level. So remember I called this 2, and this in here is 1. And then the difference, then what we see here is it's moving down, okay? And the difference here is what's happening to the energy. Instead of going in, the energy is being expelled out. A lot of everyday phenomenon, like turning on a light bulb, actually is because the electrons are excited one way, and then as the electrons fall back down, they emit light. But let's hold that thought, because it's not just any light, it's light specific to what that energy transition was. So we can actually kind of go back to our situation here, okay, but now I guess I probably have one more build. This is a setup to actually show you, maybe this is a hydrogen gas, and they're running a current through it. Electrons are being excited because of the electricity, and then as the electrons fall down, it glows, the light glows. That's exactly it. But if we were to look at that glowing light, go ahead and separate it with a prism, we actually would see that light is got these kind of awesome little bands of energies at specific wavelengths to the energy transition of the electrons around those hydrogen atoms. So down here, okay, that is a fingerprint of how the electrons transitioned as they fell back down after being excited by electricity. It is, and that's one of my points. This is a fingerprint. Fingerprint of how the electrons are around that atom. So I think that is so cool.